In this video, we're going to look at the S1 mechanism in organic chemistry. So SN1 stands for substitution, nucleophilic, unimolecular. The substitution means that we're essentially going to replace our leaving group with our nucleophile. Nucleophilic means that we're going to have a nucleophile attack. Unimolecular just means we need one molecule to get this reaction started. Comparing it with SN2 we need both the substrate and the nucleophile, whereas here we only need the substrate to get started. This is a two-step mechanism, and let's look at what each of those steps contain. Step 1 is going to be a formation of a carbocation. We're going to have our alkyl with our leaving group, typically going to be some sort of halogen. It's going to form our alkyl carbocation and our leaving group as an anion. That's the first step. After that, with our carbocation, we're going to have a nucleophile being attracted to it. Remember, nucleophile have electrons, essentially an excess electrons that they want to give away. So they would be better off giving away those electrons and forming a bond rather than keeping it just to themselves. So they're looking to bond with someone. When these two combine, we're just going to get a neutral molecule of our nucleophile and our hydrocarbon. The first step, step 1, is our slow step. It's rate determining. Our second step happens fast because we want to stabilize once we get that carbocation. Let's look at some key features of the SN1 mechanism. So the first is that we're going to have a carbocation intermediate. This means that there is a possibility of rearrangements, so either hydride, hydrogen, or methyl shifts in order to make our carbocation more stable. We want to think of our electronic effects, our inductive effects. The more methyl groups that are surrounding our carbocation, the more inductive donor effects we have, the more stable, the more electron density we have. That's where our carbocation wants to be. If you're looking at determining if there's going to be an SN1 reaction or not, look and see, once the carbocation forms, is there a more stable shift that can occur? That means that the stability for our SN1 reaction, for our alkyl group, is going to be tertiary, then secondary, then primary. We can't have an SN1 reaction with just methyl, and it'll be very unlikely to have it with primary anyway. So what you're going to see for the most part are either just tertiary carbocations or perhaps secondary, if not secondary that then rearrange into tertiary. The second feature is that it's very common for there to be reactions with weak nucleophiles. What is a weak nucleophile? It's basically a nucleophile that has electrons to give, so we do have lone pairs, but they're neutral. Our strong nucleophiles were charged, they were anions. Our weak nucleophiles, they still have lone pairs, but they're going to be neutral. The reason why they can still attack is because we have a carbocation after our first step, and to become stable, they're fine with any molecule attaching to them. The third feature is that they use polar protic solvents. So protic means that there is a chance that there is going to be hydrogen bonding. So we might see an OH, an NH group as part of our solvents. And that's okay because these polar protic solvents, they stabilize both the carbocations and the leaving groups. If you think about their polarity, we're going to have a partial positive side and the partial negative side. Well, the partial negative side can help stabilize our carbocation, and our partial positive can help stabilize our leaving group anion. The fourth feature is the stereochemistry. If you think of the shape of a carbocation being sp2 hybridized, it's going to be trigonal planar, which means that the nucleophile can attack from either the top or the bottom. This will lead us to a racemization if the carbon is chiral. So we're going to have 50% R, 50% S for the most part. Let's look at some examples. Our first one is a tert-butyl group. We have 3 methyl groups attached to our central carbon as well as a bromine. Now, we don't see any nucleophile here, we just see that and our arrow with an H2O on top of it. Well, sometimes the solvent is also the nucleophile. This is called solvolysis. And in this case, water is both our nucleophile and also our solvent. Now, we know water is a weak nucleophile because it does have lone pairs, but it's neutral. It's stable as is. We also know that this is going to undergo SN1 because if we remove our bromine, we have 3 methyl groups, 3 electron donor groups that are donating electron density to our carbocation, which makes it more stable. It eliminates some of the positive charge. Our first step here is going to be the removal of the leaving group, formation of the carbocation. We can make the first step, our product being our carbocation and our bromine anion. Our bromine is going to take those 2 electrons from that bond, leaving our tert-butyl group as a carbocation. So that's our first step. Our next step is going to be the combination with our nucleophile. So we have our carbocation down here, and then if we draw our water molecule, its lone pairs, one of them, is going to attack. And once it attacks, it's going to just attach to it. So then we end up with this final product. Let's look at this reaction. It's essentially the same thing, except one of the methyls was replaced with a hydrogen. We know this is still going to undergo SN1 because we're going to undergo solvolysis. And we know that because we don't see a nucleophile anywhere, so we know our solvent, the water, is our nucleophile. And a secondary carbocation is less stable than tertiary, but it's still stable. Our product in the first step is just going to be the removal of our halogen. And once again, our second step is just the addition of water. So we just have to have an arrow going from the electron-rich area, which is where our lone pairs are, to our electron-poor area, which is our carbocation, and then we just attach them together. So our product is just the attachment of our 2 reactants. Now, I'm not sure if I pointed this out on the last one, but when we attach our H2O molecule here, if we look at the formal charge of our oxygen, which only has 1 more lone pair, oxygen has 6 valence electrons minus 3 bonds minus 2 lone electrons. It's going to have a charge of +1. Even though our carbon is now neutral, our oxygen, which was neutral in our water, now has the positive charge. There's a sub-step that sometimes occurs. It's not really considered a third step, it's more just a sub-step of step 2, where our bromine anion that originally separated, that was our leaving group, it'll come back, and with its lone pairs, one of them will attack the hydrogen. This is deprotonation. And the bond that was between oxygen and hydrogen, those electrons are just going to be donated to the oxygen. The bromine is going to end up taking one of those hydrogens so that the oxygen becomes neutral. If I just erase this, I can erase the charge on oxygen, give it those 2 extra lone pairs from that bond, and then we also get HBr. Now, it's not only the bromine that can take the hydrogen. The water can also come back. Another water molecule can come in, take the hydrogen, and then become an H3O plus molecule. But eventually, the bromine will take the plus charge or take the hydrogen from that H3O plus, so it might be easier to just write it as the bromine taking the hydrogen from the start. Let's look at another example. Here, we have a slightly larger alkyl halide. Our first step is going to be the exact same thing. We're going to undergo SN1. That means we're going to form this carbocation. So if I separate the 2, and draw our carbocation, you might notice that the plus charge is going to be on a primary. We know it's a primary because the carbon that has the charge is only attached to one other carbon. But that carbon is tertiary. The carbon to the left, right here, is attached to 3 additional carbons. So if we can move the plus charge to this carbon, that would be a lot better for stability. What we're going to see here is we're going to see a hydride shift. We're going to have this hydrogen shift over to that carbon, making that carbon neutral, and then putting the plus charge on the tertiary carbon. Now we can rewrite this as our tertiary carbon, and then our original primary carbon that had the plus charge is neutral, and we successfully rearranged to a more stable carbocation. Now let's look at our second step. Here, we'll go with water again. But this can be anything that has essentially an OH with it, or anything that has lone pairs that is neutral. That counts as a weak nucleophile. If we attack our carbocation, we're going to end up with, once again, a positive in our H2O attachment. What we can show is that that chlorine anion can attack one of those hydrogens, the electrons go to the oxygen, and then we get HCl as an additional product, and then we put our 2 lone pairs on the oxygen, so now we just gained an OH group. What if we have a chiral carbon now? We have a Br on our wedge and the hydrogen back on the dash. It's going to be the exact same thing as before, where when we get our carbocation, we're going to be sp2 hybridized. We are only going to have 3 areas of electron density. So that means we're going to be trigonal planar. So we can remove the dash from the hydrogen, as they're all going to be on a plane. That means that when our weak nucleophile will attack, it can attack from, if you think in a 3D way, either the top or the bottom. It'll create both R and S enantiomers. We're going to end up with our racemic mixture. So let's just draw out what that looks like. It's difficult to show the 3D on the screen, but basically the H2O can attack from either the top or from the bottom. One's going to give us the wedge, the other one's going to give us the dash. Now, it's said to be a racemic mixture, but in reality, there's going to be very, very, very little more of our dashed version compared to our wedged. And that's because our bromine is leaving on the wedge. So as something else is attacking from the wedge, there's going to be very little steric hindrance, or a possibility of steric hindrance, but it's so unlikely, it might be 51 to 49, it's just said to be a racemic mixture anyway. So for our products, we're going to see one major product where our OH is on the wedge and our H is on the dash, and then we're going to see another one where our OH is on the dash and our H is on the wedge. If this video helped, please consider liking and subscribing. If you want to see how this compares to SN2, the SN2 breakdown will be linked in the description. And if you want to see how to choose between E1, E2, SN1, or SN2, I'll also link the video comparing all 4 of them in the description. Thank you so much for watching.